Okay, the second talk for today is by Dr. Nguyễn from Hanoi Institute of Mathematics. The title to the talk is Contact loci and motivic nearby cycles of non-degenerate singularities. Please.
Thank you for the introduction. Firstly, I want to thank the organizer for inviting me to give a talk in this seminar. Today I will talk about some study about the singularity of non-degenerate polynomial. And this is John work with Lê Quý Thương, the chair of my talk today. There are two parts in my talk. In the first part, I will introduce our problem, and in the second talk is about our result. So mostly we consider in this talk we consider ice to be a compressed variety, smooth compressed variety, and consider F to be a morphism from ice to C. Then and I consider so we consider at the singular point of the zero set of F. So I assume I the point in the zero set of H, in the zero set of F. Then we have the following facts proved by Minor. So here we have the zero set of F. This is a singular point at which we are considering, and we consider we take a small ball center at this point, and with radius epsilon, which is small enough, and we then we have a map to the compressed plane, and then if we take a small disk in C, then we have that. So this is the premise of the disk. Then so the first is that for any small epsilon small enough, and then for any eta which is also much smaller than epsilon, we have that the rotation of F on the so we take the premise of the punctual disk, and then we take the intersection with the ball, and then it will be locally trivial vibration on this punctual disk. And we call it the minor vibration. F at this point. The fiber of this vibration we denote by F of H. So it will be the fiber of F at the value T, and we take the intersection with the ball. Here T is small enough. So yeah. And this fiber we call it the minor fiber. Minor fiber. The minor fiber contains many information of the singularity of F. For example, when this point is an isolated singularity of F, then the middle petty number of this fiber is the multiplicity of the singularity of the singularity point of this singularity point. So this is one of the main objects in the study of the singularity of F. Also, because this vibration, we can lift by lifting the circle on this punctual disk to the ambient space, to this ambient space. Then we can obtain a so-called geometric monodromy. So we have we can call that, we can say that is the geometry of F at this point, which is a diffeomorphism of the minor fiber to itself. Yeah, so they are the main objects in the study of the singularity of F at this point. Okay, so this is the first part of the introduction. So I will say it in the Xiaomi. Okay, in the second part of the introduction, I will introduce some algebraic notion or the algebraic setting. So in this part, I will define some algebraic objects, which is which give us information of these objects, these geometric objects. So in this part, I will define the notion of the loci and which nearby cycle. Okay. Yeah. So let's here I for any S which is algebraic variety. Then I denote by var of S to be the category of the variety over S. So it is the variety over S. And so And I also define for each integer n the group scheme Nguyen, which is the group scheme of the nth roots of unity. So, and then we have a morphism from taking t to them. So we have a projective system, and then we denote by mu hat to be the inverse limit of mu. So it is. And then we so assume that S have a good action of mu hat. And I denote, we consider the, say, the rotending ring. The rotending rings of variety over S. So it denoted by K S. I should say K0 of S. So this is a talk of David Kuhn. He also mentioned some. He also mentioned about the rotending ring. So this is the abelian group generated by the symbol like so. But here we consider the morphism with kind of mu hat equivalent morphisms over S. And I should write. So I consider this is abelian group generated by this symbol, but modulo some the following relations. So there are several relations in this abelian group. So the first one is whenever we have two mu hat equivalent isomorphism, so H and Y are mu hat equivalent S isomorphic. Then the class, the symbol by X and Y are identity. And then the second relation is the relation by property. So we will have if Y is a variety subset of X, which is invariant under the action of mu hat, then we have this relation in this group. In this group. So where Y and then the third relation is about the action on the I5 bundle over S. So if we have say if we have say A, so this is the I5 bundle over X over S over H. So here mostly I consider the variety over C. So here we have C with action of say delta. Then this class will equal to the similar R5 bundle, but with the the action sigma prime, where sigma prime are the lifting of the same action on X. Yeah, so this is the rotating rings of variety of S with action of mu hat. And in this ring, I consider the symbol L, which is the class of the class of this line bundle over S, and we denote by mu M mu hat S to be the localized the localization of this of the growth ring of variety over S by L. So it will be okay. There are some notion I need in my talk. Okay, and the next the next notion I need is the following: for any n, then here so X in my talk I always fix X to be X is smooth compressed variety. Then for any positive integer n, we consider the variety, this variety to be the of X on X. So, but with this sub n, we mean that the X modulo T to the n plus 1 on X. So what is this variety? So this variety means that it is so we can say that so it is the variety such that the C rational point of this variety is exactly the C e to t plus 1, t to the n plus 1 rational point of X. Yeah. So this is so this is the idea of the notion of the space of X modulo t plus 1, t to the n plus 1. Yeah, for example, if we consider X to be the alpha space, then the the variety of so sometimes we call this variety sometimes we call this variety the variety of n of z of order n on this variety. So in this case, this variety is so it will be a affine space of the dimension and +1 e, or we can think that this space is a so we have D tuple of the, so we can say the polynomial of order of order n. Yeah. That means the every C point of this variety. So each C point, each C rational point of this variety is a D tuple of the polynomial of order n. So that is the meaning of the of one variable. Yeah, polynomial of one variable.
So I think it's polynomials of degree, not order, degree.
Yeah.
Less or equal to n. Yes.
Okay, that's right. Thank you very much.
Degree. Okay.
Yeah, the degree. And also we also have, for whenever we have the integers m bigger than n, then we have the truncated map from the space of z of order m to the space of z of order n. And then it will form a projective system. Then we denote by L of H to be the limit determining. And it's no longer a variety, but it will be a scheme. That this scheme we call it as the scheme of H on H. And in this situation, when H is an affine space, then the space of H on affine space will be the scheme of every D tuples of formal series of one variable. Okay, now I go back to my situation. So f will be a regular function on H. Then I denote for each positive integer n, then we denote n, H of n, 1 of F to be the set of arcs modulo of order of order n in X such that f of phi equal to t to the n modulo t to the n plus 1. So it will be a variety. It will be so H of n will be a compressed variety, and we call this variety is n contact loci. Okay. Also, we can define. So if we consider the width, so here for each for each point x is the zero set of f, we can consider the pull back of this variety by the inclusion map from x from this point to sorry. So I should say that so this it's easy to see that we will have an action of Nguyen on this variety. Therefore, we will have an element in the rotating ring here I denote by H0 to be the zero set of F, and then we can we will have a morphism from the contact locus of F to H0 by taking phi to phi 0. So phi 0, that means the map from the R space to the space of the 0. So, yeah. So, and then we will have an element in the rotating ring of the variety of the zero set of F with the action of mu hat. And here we can, yeah, and similarly for each point, we can define the similar variety. So I denote by Xn 1X. So maybe for and X, so this is the point. F is the set of the arcs modulo n, such that we still have the equality, but we require that this arc starts from this point, and by the same region we can see that this variety we call it variety of so this is the contact locus of F at this point, at the point X. And we also have the action of Nguyen on this variety, and we also have the morphism from this variety to the zero set of F. Therefore, we also have that this variety give us an element in this rotating ring. And then we will define a formal series denoted by this, which is the sum of this form. So N1 F L to the minus ND. So this D is here. D is the dimension of of H, and then T to the N. Here N is great, is positive, and we call it is a motivic zeta function of F. We all we also have the motivic zeta function of F at the point F at H. So, and it's proved by the depth and logic that these two series is rational. Rational means that this series belong to the is a kind of polynomial of polynomials with the coefficient in this ring, and the variable is the finite number of the following. So B to the B. So and A, B is some pairs of integer number where B is required to be positive. So this is the meaning of the rational series. So by this result, we can take the limit . So we can take the limit. Limit is some morphism such that so the limit when t go to infinity, and this is some morphism such that we have that equal to -1. So the limit is some some morphism such that we have this equation. And then we can define S of f to be the minus of this limit, which we call the Motivich nearby cycle. Of f, and SF of h we define to be the minus of the limit of this series. So we call it the Motivich minor fiber of the function at this point. And what is interesting is this notion is that those notions have a very close relation with the minor fiber, which I defined at the beginning. Meaning that if we take the topological Euler characteristics of this minor fiber, it will coincide with the topological Euler characteristics of the minor fiber of f at this point. And also, if we take the Euler characteristics of the contact loci, and so this is the contact locus of f at this point of the point h. Then if we take the Euler characteristics of this variety, it will be equal to the, oh, I forgot to define it, to define the left set number. So it is the n left set number of the monodromy. So it will be defined to be, so we have phi to be the monodromy, the geometric topology, geometric monodromy of the minor fiber. So it defined to be the alternating sum of the trace. So we take the cohomology of phi to the end. So this is the induced phi on the cohomology group of the minor fiber. It will be so Q, this is Q of the minor fiber. We can take that's the compression coefficient, to itself. And this left set number measures the number of the, in some sense, this left set number measures the number of the fixed point of the monodromy. And it is also an invariance of the singularity of f. Okay, by this theorem, we can see that these two objects bring many information of the singularity of f, and it is the object in our study. So the aim, the purpose of my talk is to give some calculation for. So we study the contact loci and also the nearby cycle. So nearby cycle is defined over there. And we study these two objects for F to be non-degenerate. This is the purpose of my talk. More precisely, we try to give some to give an explicit formula for the nearby cycle, and also with some try to give some study on the cohomology of this variety. That is the purpose of my talk. Okay, now I will talk about our results. So in our work, we mostly consider the say the polynomial of and of compressed coefficient in a B variable. So F is a polynomial. So we can write so F like the sum of the D, and we will have kind of a Newton polyhedral of F. Which is the convection of the union of the alpha with sum of alpha with the first but alpha, we take alpha such that the coefficient in the function is non-zero. This is a Newton diagram of the function f, and we have the notion of the for each phase, you can say phase of gamma. Phase is it's a part of the boundary of gamma. Then we have phase function, I denote by f of gamma, which is part of f, such that the exponent of the monomial appearing in the function belong to this phase. So it is the sum of where alpha belongs to this phase. So this is the phase function of f, and we say that f is non-degenerate with respect to this phase gamma if the zero set of this phase function has no singularity in C start with a D. Has no singularity in okay. So, as I said, we want to study this space, this variety. And in order to study this is a space of arcs of order n, such that the order of f equal to n, like that. And in order to study this variety, we try to stratify this space into the union of some subspace, which is easier to study. So okay, so so for each J to be a subset of this set, and for each point each point A is in A is the tip of the point of the integer point. We denote by Hj n. So n is it's fixed. It's a fixed integer. This is the subvariety of the contact locus. It will be the set of arcs or so at the of f, such that so phi will be, so each for each element in this each point in this variety, each point in this variety, it is a tuple, d tuple of polynomial of degree at most n. So this phi will be the tuple of d polynomial of degree at most n. Then we can say about the degree. We can say about the order of the polynomial when it's non-zero. So this J is a set. It's the set of the indices at which the component is 0. So phi I t equal to 0 if I is not in J. And for the rest, I require that the order of phi J equal to AI. So A here will be A1, Aj, where J is in J. If J is in J. Okay, so this will be a constructible subset of the contact locus. And we have that. We have the following. We have that and of course we can put here if we can consider the if we consider the arc starting at this point, then we have ice here, and we require, of course, and we have the fact that the contact locus will be the disjoint union of all of these subsets for any J and A. So I will not say what is the set of the indices here. And what we obtain is that we can describe very explicitly this subset. It is our first main result. How much time do I have left? 10?
Maybe 10 minutes, please.
So I will go
10
quickly.
minutes. Yeah.
Okay, I will skip something in my talk, but what I want to say is that this subset is we can describe very explicitly this subset. We prove that this subset is I need to define something. So for each phase gamma of the Newton polyhedral of F, we have H gamma 1 to be the variety defined by the equation. This is the G gamma. G gamma means the number of the, so I will say that 1. So J gamma is the number of the effective variables of F gamma. So we only count the number of the variables of this phase function. It's the real phase function. At H gamma 0. And yeah. Okay, then the first theorem is the following. We have that the contact loci. We have assume F is non-degenerate, but we need it to be non-degenerate with respect to all phase of gamma. Then so this is the first part. Then we have the formula of the nearby cycle of F, which is the following. Sum of to the D minus where the sum is taking we take all the sum with all phase. And this lambda gamma is some integer number which is defined in terms of the combinatorial information of F. So yeah, I can write the equation, but you don't need to understand what is the formula. It's quite complicated. Something. Yeah. But it is computed in terms of the Newton diagram, Newton polyhedron of the function. So, it's subset. So it is some you can just know that it is some integer number. Yeah. So this is a formula of the nearby cycle of F. And in the second part, from the first part, you can. So in the second part, we don't need F to be non-degenerate with respect to all phase. We only need that F we assume that F is non-degenerate with respect to all compact phase. Then we have the formula for the motivic minor fiber of F to be so the formula will be on compact phase. Không cần compact, có cả chứ. Có thể cả cái lực độ Newton đây. Cái điều kiện 1 khá mạnh. Okay, so this is the first result. So that is the first result in our study, and công thức thì giống hệt. Công thức này thì chưa có ai có cả. Công thức này thì chưa có ai đưa ra công thức cho cái nearby cycle này cả. Anh chưa nhìn thấy. Niket chỉ viết được hàm zeta chứ không có tính lim. Không tính lim. Okay, I want to remark that the second part of this theorem is known by many authors. It is proved by firstly by Steinbring, and then second by many people prove the second formula. But okay, and in the last part, I will introduce our study about the cohomology of the contact load track. So I want to say that nó hơi lằng nhằng, tức là thì cũng là cái lấy tất cả các cái phase của nó, kể cả phase, kể cả điểm nữa, kể cả đốt, nhưng mà trong đốt cái này thì có thể là không có, nhưng cái nào một thì có, lấy cả. Không, lấy tất, lấy cả những cái điểm này nữa, lấy tất cả các compact phase. Ra lại thằng nào? Okay, if you have any question, please ask. Yeah. Okay.
Now you have 3 minutes.
3 minutes. Okay. Okay, so maybe I go through the second part of my talk. Is so we also assume that F is non-degenerate, but in the sense of Kuznets code, that means non-degenerate with respect to all compact phase. And we assume that F, so we will assume that the origin belongs to the zero set of F, and then we will consider in this theorem we will consider the cohomology of the contact load side of F at this point. And what we obtain is that we will let F be any shift of abelian groups on, we can say on the space. No. So on C to the D, and then we have there's an exact sequence. There's a spectral sequence. Which converts to the cohomology group of the contact loci. So the first base will be the direction of on. So this is P of the AGEA. Yeah, and F with the coefficient in F converging to the cohomology group of compact support of the contact loci of F at this point, where the sum here, we take on the J A such that the dimension of this space equal to Q. Let me confirm it. Yeah. Sorry, ZDP plus Q. Yeah, and in order to prove this theorem, we use a kind of filtration of the CF, and then I want to remark that this subvariety is easily to compute the cohomology. So I don't explain in my explicitly in my talk, but this set is very easy to compute the cohomology. Okay, that is the end of my talk. Thank you very much.
Yeah, thank you very much for the talk. Any question?
Hello? Can I ask you a question? Okay. So can I ask what is the main reason you consider the non-degenerate polynomial? I know that non-degenerate polynomial maybe is the easiest case, but can you handle the singularity of the intersection there?
Yeah, we consider the reason we consider the non-degenerate case is that it's easy to compute. In some sense, it's the most simple singularity. That is
yeah, I know. It looks like Chan Perso case to me, and I think if you want to consider the singular case, you may need to introduce some configuration space to remember the singularity. So I think you can try to do the singular case.
Yeah. Okay.
So, more question?
So your framework is K-theory. I'm asking, do we do something for homology instead of K-theory?
Yeah, sorry that I don't know anything about K-theories, and maybe I could not understand your question. Could you say ask again?
So your framework is K-theory. I want to see other similar thing for homology.
Yeah, maybe I cannot I cannot answer the question because it is I don't know. I don't see the relation between this variety and case theories, and I don't know about. Yeah, so I don't know. Then I cannot answer you.
Any more question? So if no more question, let's thank speaker again.